Let me begin by clearing up the minus signs. So I just want to compare Anderson and Weinberg, since we're using both texts. Anderson has plus, 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 minus. Weinberg has minus, plus, plus, plus. Sorry?
Plus minus minus minus. We should label those coordinates.
Okay. Yeah, let me write exactly what he has. Yeah. That's my eraser. Okay. As a result of which, some formulae have different signs. So Anderson has 1 over 16 pi g integral d4x square root minus g r minus 2 lambda. And Weinberg has minus 1 over 16 pi g integral d4x root minus g. And I think he would have to have, therefore, a plus. They both have g mu nu is minus 8 pi g t mu nu. And this would be plus lambda for Anderson and minus lambda for Weinberg. The Riemann tensor in both cases is the same. Some authors have a change in sign. Some authors use the opposite sign, which is another source of confusion. But they have the same sign. And one difference here is for a scalar field. Starts with a plus here, whereas for Weinberg, it would have a minus. But for Maxwell, it's the same in both. And the reason it's the same in both for Maxwell is you need two metrics to raise the indices here. You only need one here. So the scalar flips sign, but the vector doesn't. So this explains the variation we had yesterday, that Anderson would have T mu nu delta G mu nu like this, and Weinberg would have a plus. So my apologies if we mixed up the two yesterday. So we started talking about Lagrangians, scalar Lagrangians, vector Lagrangians, and we had this principle which is called minimal substitution. Which just says you take your flat space theory, and everywhere you see an eta, you replace it by a G. Yeah. I'm sorry? A 2. Yes. Thank you. Any other questions? Minimal substitution says everywhere you see a Minkowski metric, you replace it by a Riemannian metric, and everywhere you see an ordinary derivative, replace it by a covariant one. Now that guarantees that your equation is generally covariant. It doesn't guarantee that it's right. You could add other terms which are consistent with general covariance. And so there's no real theorem that says minimal substitution is the right recipe. But frequently that's what we do. Let me give you an example of non-minimal. Remember, for a scalar field, the minimal Lagrangian was G mu nu, d mu phi, d nu phi, minus m squared, phi squared. That's what this rule would tell you to do. But you frequently see in the literature a non-minimal term that looks like this. Now, there's still only two derivatives. But this term could be there or it might not be there. Minimal substitution would say it's not there, but there's no, as I said, rigorous theorem that that's a good principle. It's equally generally covariant. Both ways have two derivatives. One of the reasons why people like this is that in the case where the mass is 0, and in the case where this factor equals 1/6, there's a symmetry known as conformal invariance. Namely, if we rescale the metric by an arbitrary function of x, the action remains invariant. So this is a new symmetry over and above general covariance, which this Lagrangian would have. And the Maxwell Lagrangian has it. And the Dirac Lagrangian, when we come to do spinors, also has it if the fields are massless. But Einstein's theory itself does not have this symmetry. So its status in the world is still a matter of debate. Penrose, for example, likes to think that the world is conformal invariant and only looks non-conformal invariant. So there's lots of interesting work been done on that, but I just mention it in the context of if you want to have a scalar field that's conformally invariant, you have to have this non-minimal coupling. So that's something which is quite tolerable. Let me give you one that people don't like. We could take the Maxwell Lagrangian and add a term R mu nu rho sigma F mu nu F rho sigma. Again, that's perfectly generally covariant. It doesn't respect this, but worse, it has 4 derivatives, because this already has 2. And we've got another more derivatives here. So that is not favored. And similarly for gravity itself, you could say, well, let's have some r squared, or some r mu nu squared, or some r mu nu rho sigma squared. But there again, they would involve more derivatives. Now, there's a problem with more derivatives, is that if you look how these fields propagate, if you only have 2 derivatives, they propagate sensibly with positive energy and so on. If you have higher derivatives, there's a danger you can have what are called ghosts, which are things with the negative energy that we don't like. And that's another reason for not looking at terms like that. Now, you may, however, if you're reading current literature, see people talking about such terms. So what are they doing if there's ghosts? Well, the attitude in the quantum theory is that Einstein's theory is not the ultimate description of gravity. It's the right description at low energies, but at very high energies, approaching the Planck energy, you have to replace it by something else. String theory maybe, or put in your favorite theory. And in this case, Lagrangians like this are really just a low energy approximation to that fundamental theory. And so, if they're a low energy approximation, if the mass of these ghosts is higher than the energy range in which you're making the approximation, then it's not a problem, because your theory is only valid at low energies. So classically, we don't put in higher derivatives unless we want to be conformal in the case of a scalar. And then it's only two derivatives still. And in the quantum theory, we do put them in, but with that proviso that this is not then the ultimate theory, but rather some low energy limit. Now, this has a bearing on what we said about first and second order formalisms, because you remember in the second order formalism, we have an action that depends just on the metric and possibly some matter fields. Whereas in the first order formalism, we have a metric and gamma and the matter fields. And we treat them independently. Now, let S stand for gravity plus matter. If our matter Lagrangian does not depend on gamma, then everything proceeds as it did for pure gravity. The equation of motion for gamma is, let's write it, I know how, what makes it a bit clearer. This is gravity depends on G, matter depends on G and psi. Here, gravity depends on G and gamma. Now, here we have a possible difference. The matter Lagrangian could depend only on G, in which case the equation for gamma is that it's the usual expression in terms of G and its derivative. But if you were perverse, you might say, well, why don't we allow the matter Lagrangian to depend on gamma as well? General covariance doesn't forbid it. But now there's a difference, because when you vary with respect to gamma, you could pick up extra terms. Unusual. So these two theories would, in fact, be different physical theories. And it's up to you to decide which one you like the best, but they would be different in that case. In fact, I was thinking just this morning, and if anyone's interested in, got a few minutes, what would happen if we made this R of gamma rather than R of G? Would that change the theory? I think it would. Something that you never see in the textbooks, but might be worth looking at as an exercise. .5, 4.5 is Brans-Dicke. We mentioned in the context of experimental tests that there was an alternative to Einstein's theory, which has fallen out of favor, but which is interesting for purposes of comparison. And it was related to the idea that Newton's constant, or at least some appropriate dimensionless combination of Newton's constant and the Planck mass and some other mass, could vary in space and time. And this is achieved by putting a scalar field phi in front of the Einstein term. Now, once you've introduced a scalar field, you need its own Lagrangian, and they chose to write it like this, where omega is some constant parameter. However, to preserve the equivalence principle, they said, let's take the Lagrangian to depend only on G and the matter fields, but not on this extra field phi. So matter just sees the metric, but there's this extra term, and we can write down its field equations. G mu nu is minus 8 pi, and I'm putting this is Weinberg's version, so there may be a factor of kappa different, but let's live with it. Box is grad mu. That's the Einstein equation. And then there's a phi equation. Which is the trace of the energy momentum tensor. So you see, in appropriate units, phi is playing the role of a space and time dependent Newton's constant. And that was one of the motives in writing down this theory. And it's still the case that most of the theories that we like, supergravity, string theory, other attempts at unified theories, tend to have scalar fields in them. And if they're massless, that's a problem, because you could end up disagreeing with the experimental tests in the same way that Brans-Dicke theory does. You can avoid that problem if your scalar field gets a mass, which is sufficiently heavy. So that's a sort of constraint, if you like, on attempts to unify gravity with the other forces. You want to make sure that you don't have massless scalars that would spoil the agreement with the experimental tests. So that concludes section 4, but there's another little diversion that may be useful. Yes, it will be useful because I want to discuss symmetries, and before concluding this section I wanted to discuss symmetries and conservation laws. So the diversion is on the topic of functional derivatives. This is a quick, neat way of getting field equations, and it's very convenient when you come to talk about conservation laws. So let me just spend a few minutes talking about functional differentiation. The action principle depends on the fields and their derivatives. And that's what we call the functionale of the fields. So let capital F square brackets little f be a functionale of a function phi. And the typical case we're going to be looking at is where S is the action and phi are the fields, and F are the fields. Then the functional derivative of F with respect to F is defined to be whatever sits there in the variation. Equivalently, you can define it like the way you do ordinary differentiation. As the limit as epsilon goes to 0 of the functional f of y plus epsilon delta of x and y, and that's a Kronecker, a Dirac delta function, minus f of y over epsilon. Example, if f is f itself, delta f of x, delta f of y is just delta of x comma y. And delta f equals 0 if f is independent of y, of f. Similarly, if f of f equals the integral d4x, or integral d4y, let's say a of x and y, f of y, then delta f of z is a of x and z. It commutes with differentiation. So the functional derivative of something, the functional derivative of a derivative is the derivative of the functional, so that is true. And other rules are the same. As ordinary differentiation. For example, delta f of z is the integral dy, delta phi of f of y, delta f of z times delta f delta phi f of y. So the usual chain rule holds. And we can also Taylor expand. So a function now of f plus the small deviation is f of f plus the integral d4x delta f of x times h of x plus 1 over 2 factorial integral d4x integral d4y delta 2f delta f of x delta f of y h of x h of y plus dot dot dot. Now if we have a functional of two variables, and we do the obvious thing, we have one term for f and another term for g. Now, why is all this useful? Well, using the rules that I've just given you, if I differentiate Einstein's action functionally with respect to g mu nu, I get 1 over 16 pi g root minus g r mu nu minus 1/2 g mu nu r. And if I differentiate the matter Lagrangian with respect to g mu nu, I get minus 1/2 g mu nu T mu nu. So we can neatly summarize the energy momentum tensor as the functional derivative of the matter action with respect to the metric. In fact, we can even define the energy momentum tensor that way. And the Einstein equations are just given by putting the functional derivative of the total action equal to 0. So delta S, delta G mu nu equals 0 equals R mu nu minus 1/2 G mu nu R plus 8 pi G T mu nu is equal to 0. By the same token, the functional derivative of the action with respect to whatever other fields may be there give the equations of motion of the other fields. Note that what you get has a root minus g in front, so the functional derivative of the action is the tensor density of weight 1.
When you said the delta S that pi equals 0, and then in the next line you've got the plus 8 pi gt, you just meant to follow on from the equation you wrote before.
This one?
No, above it. Above.
This one.
Yeah. Does that come from what you just wrote over?
Should do, yes. You're going to tell me there's a minus sign somewhere.
No, in the bracket. In the bracket?
The S here is the sum of the two. Yes, thank you. That should be upstairs. Let's just give a quick example of how useful this is. Let's do one in flat space to start with. Let's take Maxwell plus a charged scalar field. So we have the Maxwell action, then we have the matter action, which depends on A, and a charged scalar field is complex, field phi, so it depends on phi and its complex conjugate. The Maxwell Lagrangian is the usual one, and we're in flat space, so we don't need the root minus g. and the charged scalar, because it's charged, there's no factor of a half. But we need a covariant derivative in the Maxwell sense, d mu minus IE A mu phi, and grad mu phi star is d mu plus IE A mu phi star, and E is the charge. Now, what's the symmetry of this Lagrangian? Well, the Maxwell piece we know already is invariant under changing A by the derivative of some scalar field alpha. And the rest will also be invariant under that, provided phi goes to e to the IE alpha times phi, and phi star goes to e to the minus IE alpha phi star. Now, the reason for this covariant derivative is that it transforms in a nice way. The ordinary derivative does not transform in a nice way, neither does the second term, but this combination ensures that this Lagrangian has the right symmetry. Now we can see why functional derivatives are useful. The electromagnetic current, which is the Maxwell analog of the energy momentum tensor, if you like, which we call J mu, is just the derivative of the matter action with respect to A mu. And it equals IE phi star grad mu phi minus grad mu phi phi star. So if we vary the entire action with respect to A mu and put it equal to 0, we get minus d mu f mu nu plus j mu is equal to 0. So varying with respect to A gives us the Maxwell theory with the source term. And similarly, varying with respect to phi and phi star, and with respect to phi, gives us the equations for the fields. Now you notice d mu, j mu equals 0 as a consequence of the field equations. As a consequence of these equations, you can check that the divergence of J mu is equal to 0. But that's also required by the Bianchi identity which said, if you remember, d mu, d nu, f mu nu is identically equal to 0. So this is the electromagnetic analog of the divergence of Einstein tensor being related to the divergence of the energy momentum tensor being 0. And here we have the divergence of d mu f and the vanishing of J being related in a similar way. Why don't we have a mass term? Yes, we could have put in a mass term. Just for simplicity, I could have put in an m squared, phi squared term if you want. I just left it out to keep things simple. Now, J mu is conserved in the ordinary sense. The ordinary derivative of J is 0. And physically, that's because photons are themselves electrically neutral. They don't interact with themselves. This is not true when you come to Yang-Mills fields like W bosons and so on. They do interact with themselves, and in that case, you'd need a covariant derivative on J. But for Maxwell fields, they don't interact with themselves, and that's an ordinary derivative. Similarly, for gravity, gravity interacts with itself, so the stress tensor will be covariantly conserved. Now, the main virtue of the functional derivative is that it allows us to discuss the relation between symmetries and conservation laws. Let's look at the example we've just looked at. Delta S is delta S, delta A mu equals 0. Let's look at the case where delta A mu is a gauge transformation. So I'm not looking at arbitrary variations now. I'm looking at gauge transformations. And this statement says my action is gauge invariant if I put it equal to 0. But a gauge transformation is d mu alpha. So if I put that together, and I integrate by parts, I learn that d mu delta S delta A mu times alpha is equal to 0. But since alpha was arbitrary, so this is the Bianchi identity. If the action is the Maxwell action. And when S is the matter action, I learn that d mu j mu is 0. So you see, we've abstracted from this particular example a general rule that any action, doesn't matter if it's this one, some other one you might dream up, which has a gauge invariance, whatever it may be, this has to be true. And whatever the matter action may be, if it has a gauge invariance, this has to be true. So, invariance of the action under gauge transformations implies conservation. The current has to be conserved as a consequence of the gauge invariance. So let's now, after that toy example, go back to the case we're really interested in, which is gravity. So let's take the gravitational part of the action and consider a general coordinate transformation grad mu epsilon nu plus grad mu epsilon mu. You remember that was the infinitesimal form of the coordinate transformation, and it's the analog of delta A mu is d mu alpha for electromagnetism. We plug this in here and integrate by parts again. And we find that the integral d4x of the covariant derivative delta s delta g mu nu epsilon nu plus grad nu delta s delta g mu nu epsilon mu is 0 if the action is generally covariant. And since epsilon is arbitrary, this means that grad mu delta s delta g mu nu is equal to 0. This is Bianchi again. Now, the example we're familiar with is where this is the curvature scalar, but it's true for whatever. This could be anything, just so long as it's generally covariant. That has to be true. Yeah?
Why do we not have the square root of minus?
Because the definition of the functional derivative. Sorry, here I do need it, yes. Thank you. I don't have it here because that's the definition of the functional derivative, but I do have it here. Thank you. No, I don't have it there. I'm sorry. This is remember delta S delta G was the density of weight 1. So it's already of weight 1. I don't need the root G. And if we apply it to delta SM, we learn that the energy momentum tensor has to be equal to 0. So the functional derivatives are useful not only for deriving field equations in a neat way. Field equations are just, you take your action, you functionally differentiate it with respect to the fields, you put it equal to 0, that's your field equation. But they also help you understand the origin of symmetries and conservation laws. So the remaining part of this section, before we move on to cosmology, is Vierbeins and spinors. So let me begin by saying a little bit about the Vierbein formalism. The world is made up of bosons and fermions, and so far we've only discussed bosons. So there's a big gap in our analysis. Bosons have integer spin and obey Bose-Einstein statistics. Fermions have half integer spin and obey Fermi-Dirac statistics. In particular, they obey the Pauli exclusion principle. And so far, we've dealt with tensors, scalars, vectors, higher rank tensors. But fermions aren't described by tensors, they're described by spinors. Spinor representations of the Lorentz group in flat space-time. And this presents difficulties, or a challenge at least, for coupling to gravity, because all the rules we've developed are about tensors. And now we've got a new animal, spinors, to contend with. And this is what the Vierbein formalism addresses. Now, Weinberg, as always, likes to talk about the freely falling frame. I'm not sure this is the best way of introducing it, but he likes it, so. So you could call this E mu alpha of x, E nu beta of x, eta alpha beta, where E mu alpha of x is the derivative psi alpha dx mu of x evaluated at this special point, local point x. But in fact, we didn't need the local frame to write that. We could write this anyway, provided this index alpha is a Lorentz index. So we've got E mu naught, E mu 1, E mu 2, E mu 3. You can regard them as 4 vectors. Under general coordinate transformations. So E A prime of x prime is dx nu dx prime mu E A nu of x. So as far as their mu index is concerned, they transform as vectors. And we can raise and lower indices E A mu, and I'm change my alphas to A's, let me call them alphas. E alpha mu is G mu nu E alpha nu. But what about the alpha index? This is in the flat space, or what we call the tangent space. Eta mu nu, you remember, is what's left invariant by Lorentz transformations. So I can make a Lorentz transformation on the index alpha and another one on the index beta. And this won't change because eta alpha beta is the invariant tensor for the Lorentz transformation. So we're going to say E mu, let's call it alpha. Let me be consistent with putting the alpha index first and the Greek one second. So this has two kinds of transformation rule. Transforms as a vector that we're familiar with under general coordinate transformations, but it transforms as a flat space vector, sort of, under Lorentz transformations. But the difference in general relativity is that we're going to allow the Lorentz transformation to be a local transformation. We're going to allow the parameters to be different at different points in space-time. So we raise and lower indices with etas. So E alpha mu is eta alpha beta E beta mu. And E A mu E alpha nu G mu nu is eta alpha beta. So, roughly speaking, E is the square root of G. So this means that G mu nu remains unchanged under a Lorentz transformation. And the other useful role played by the Vierbein is you can trade in one kind of index for another. So suppose I have some tensor T mu nu rho. I can multiply it by 3 and I should say these are called Vierbeins. From the German, 4 legs. Vierbein. And can convert with a bunch of Vierbeins you can convert it to a tensor that has only alpha, beta, gamma indices. So I'm using the beginning of the Greek alphabet, alpha, beta, gamma, and some authors use the Latin alphabet ABC to refer to the Lorentz part of the story, and the middle of the alphabet, mu, nu, rho, to refer to the usual general covariant part of the story. And I can use a Vierbein to convert one of these indices. So this is the tensor under general coordinate transformations. I convert it into something which is a scalar under coordinate transformations, but transforms as a rank 3 tensor under what are called local Lorentz transformations. Local because they're different at different points in space-time. Now, note so I can describe gravity. I could, in fact, forget that I've ever heard of G mu nu, if I wanted to, and describe gravity by this fellow here. But note that it has 4x4 components. Versus the 10 of G mu nu. So I've overdetermined the system, and that's as it should be, because I have the freedom to make Lorentz transformations on this fellow. So everything fits together. So when it comes to ordinary gravity, it's a luxury. I can either describe it by the metric tensor, or I could describe it by a Vierbein. It's entirely up to me. Where it doesn't become a luxury but a necessity is when we want to couple to fermions, which we'll do tomorrow quickly. Because only with the Vierbein can we couple to spinors. Yeah.
To your right.
Here?
Right. The sentence.
E is the square root of G. Well, this is just a hand-waving expression to say that E is the square root of G. And this equation is the same in both. This equation is the same in both signatures. So it's the square root of G in Anderson's signature, and it's the square root of G in Weinberg's signature. Yeah?
Do you mean for fermion we use the E rather than G to do the raising and lowering indices?
Well, we'll see tomorrow how we deal with fermions.
Does the fermion obey the geodesic equation?
No, point particles obey the geodesic equation. So there are ways of describing point particles with spin. You can augment the geodesic equation with some spin terms, but that's not really the way we describe fermions. We describe fermions by the Dirac equation. Yeah. So when I say we're going to talk about fermions, I mean we're going to talk about the Dirac equation in curved space-time.